All right, the vertical line test. It's a way to quickly check to see if a graph is a function. And I'm not even going to do with an example with this because it is so simple. So some of the questions, they might have a graph already there for you. Sometimes you have to make the graph yourself. But all you're going to do is draw a vertical line. And for this one, I'm going to draw a bunch of vertical lines. If you notice, it only ever intersects the graph once. So it's a function. For this next one here, I draw a vertical line there. Doesn't even hit the function, but that's okay. That's not the problem. The problem is here when I draw one vertical line and I see it hits the function twice. That tells me it's not a function. So if it's a graph, and you can just do this with a pencil. Sometimes I just draw, like I hold my pencil and just run right over because it's a nice straight line that I don't have to draw over and over again. Not a function because it hits the graph twice. The last one's a little bit different, and it's got something that's kind of unique on it. It's got two horizontal lines, and if you drew a bunch of vertical lines on it, you could see on either side of that, totally fine. It's a function. But the question is what's happening right in the middle there. If I draw a vertical line on it, it looks like it hits it twice. But let me draw a zoomed in view of this. So the bottom one comes in, and it's a nice big solid dot. And then the one above it is a big open dot, and then it continues on to the right. So what's happening here is that open dot means, hey, it approaches that point and gets really close to it, but we don't actually count that point. And then you draw your vertical line through it, and you can see it's only hitting the graph once at the bottom spot because it's going through that open point in the spot above it. So this is called an open endpoint. And if a vertical line goes through an open endpoint and a closed endpoint at the same time, then you're okay. It's still a function. It's when it goes through 2 points of the graph at the same time and one of them isn't open, that's when you've got a problem. So, like I said, I basically just did what the examples would be, but with explaining the problem. So the examples are going to look just like that. You just might have to plot the points first. That's the only thing that would be different about it. All right. Now let's talk about functions, and we've talked about them in terms of how they visually look, or maybe look with a mapping or with a set of points or a table of values. I want to talk about what they look like with equations. Here we have an equation with two variables, y equals 3x minus 8, and that's basically relating the variable x to the variable y. Now functions, and this one is a function, we sometimes want to write them in something called function notation because it gives us a lot of options on how to calculate stuff out very nicely and how to write and represent these things really well. Basically what you do is you take the output, here in this case it's y, and I'm going to say y equals a function f of x. So this is, I say, f of x. And this f here is just the name of the function. Lots of times we just use some sort of another letter. It's like another variable, except it's just the name this time. And you can see in the examples we'll do in a second, it's usually a cursive lowercase letter. Sometimes it's capital. But it's not a variable in itself. It's just a name of a complete function. So the idea here is y equals f of x, but we know that y equals 3x minus 8. And this is where the transitive property comes in. This is really telling us that f of x equals 3x minus 8. So you can see they look almost exactly the same, but the function notation has some advantages. Whatever's in the x is the input, right? So when I go to try to evaluate these functions, like I'm going to do on example 4, f of x equals negative 4x plus 7, and we're going to try to find each value. So what I'm reading here is f of 2 is how I'd read that out loud. And what that means is f of 2, everywhere where I see an x, I'm going to make it a 2. It's telling me right away, hey, you got this function, plug in 2 for all the x's. And then I can evaluate it. Negative 4 times 2 is negative 8 plus 7, and that equals negative 1. So f of 2 equals negative 1. Now what's important about that is the function f equals y. So really what this is telling me is I have the coordinate 2, negative 1 is part of my function. And because the function is kind of just using a name, I can use it with other expressions. F of negative 3 plus 1. This is really saying f of negative 3 plus 1. That's how I say that verbally. I'm going to evaluate the function for negative 3 and then add 1 into it. Well, I know the function of negative 3 is negative 4 times negative 3 plus 7. All that right there, that is all f of negative 3. And then I'm just going to add in the plus 1 at the end. Negative 4 times negative 3 is positive 12, plus 7 plus 1. Well, all of that together is 20. So f of negative 3 plus 1 equals 20. It's just a new way to manipulate expressions. It's not without purpose. Basically, everything you do in math is all based on functions from now on. It's not completely true, but a lot of the things are functions. So we like to have ways to manipulate them without having to rely on what could be considered a slower way of doing it. All right. Here are some nonlinear functions. And by nonlinear, it means it's not a straight line. You know what? I'm going to do these on the next video. So that way you can take a little break if you need to.